some new pieces of modern astronomical technology to try out. And the reason they were so interested is because it had come to light that the sun has a corona, right? An area around it where things are being injected into space, and it's incredibly hard to see that when the sun is actually out, because the sun is very bright, right? So it made it impossible to actually study the corona of the sun while the sun was in the sky. And this is a problem, right? But a total solar eclipse changes that, because the moon blocks out the sun and leaves the corona. And so over a very brief span of time, you can make astronomical measurements of what surrounds the sun. So this was so important that an entire Tennant here from, there it is, J.F. Tennant of Great Britain. And there's an entire novel, basically, written in the first person of his account that he reported back to the monarchy and to the Royal Astronomical Society in Britain. And I want to read you just a little bit of this preface here, because I think it's really interesting. He says, observations of the total eclipse of August 17, 1868 were deemed so important that the Astronomer Royal, with the concurrence of the Council of the Royal Astronomical Society, addressed the Secretary of State for India on the subject and recommended that preparation should be made. It was ultimately determined that the expense, very important in all science, who's going to pay for it, be borne jointly by the government of India and the imperial government. And I was appointed to experience the operations. Superintend the operation. Sorry, my eyes are going. So the modes of the observations were to be threefold. First, the spectroscope was to be used to examine the corona and prominences as to their source of light. So what they were interested in is what is actually giving the prominences, the corona of the sun, their light, right? Is it reflected starlight from the sun itself, or is it something in the corona itself that is glowing? And this is a question that they could not answer yet. And this is something they tried to figure out. Second, the polarization of the light of the corona and prominences was to be examined. Polarization of light, also something that was new and a hot topic at the time. And finally, several photographs were, if possible, to be taken in the absence of the sun. So this first one here is the most important to our story, right? This idea of the spectroscope. So this is actually a sketch of the very modern, very expensive, and very high-tech telescope that they were using at the time. That's not being facetious. This thing is incredible, right? This is the late 1800s, right? And massive high-powered telescopes available here. And they were using this new technology, the spectroscope. This is an actual sketch from his expedition log here, and this is a device that was used to separate the light into its individual component colors so they could examine each color or wavelength of light given off by the sun and its corona and see what light, maybe there was some extra from the glowing material, or maybe it was missing something. Right? So the spectroscope consisted of 4 parts. There was a coupler here at the top to interface with the telescope directly, a prism to diffract the light in the middle right there, that center circular part. There was a port to inject a calibrated scale, because you wanted to know what wavelengths you were looking at. And this was hard, so you're superimposing a scale onto this image that you're seeing here, and then an eyepiece with which to view it. So this piece of technology was radically new at the time. And in fact, the idea of separating out light at all and using that to probe the composition of anything was pretty brand new. It only went back a few decades to this place here. This is Benedictburen. This is a place where a guy by the name of Joseph von Fraunhofer was studying. So Benedictburen was a Benedictine monk monastery, and they were really interested in the fabrication of new optical devices, and Fraunhofer was here working on it. And what he discovered was a way to build the first modern spectroscope, a way to split the wavelengths of light. Now that was interesting. He could make a rainbow at will. Very cool. But what he found was, actually here I have a sketch. It's an actual sketch of him demonstrating his new device to all of the important people around. But what he found was when he dispersed the light with a prism and examined the light of a flame, and he eventually would do this looking at stars as well, he saw dark lines cut out of the rainbow, right? Now, even though quantum mechanics and our modern understanding of the structure of the atom allows us to understand, and we'll get to it, exactly what these lines are, right? He had already figured out that these lines indicated the presence of specific elements, specific compounds and specific types of atoms, right? Because he could isolate those. They were already able to isolate some of the elements and burn them in flames and see which particular lines were cut out of that spectrum. So that made the spectroscope a really powerful analytical tool. They could take something, burn it, and figure out what it was made of just by looking at the light. That also meant that they could look at the light of other stars. And if the lines were cut out of the light from that star, and they matched the lines that were being cut out of the light of the flame, then they could say, well, calcium and sulfur and sodium and potassium were in those stars, those distant stars, which is a really incredibly powerful technique. Now, they had no idea what was causing this signal, though, right? We, of course, now know that what's happening here is that the structure of the atom is giving rise to this. The atom is a positively charged nucleus, and it's surrounded by electrons. And as you put energy in, light of different colors and wavelengths, you move those electrons around. You give them more energy, and when they take that energy in, they absorb that light, right? They block it out, and you give rise to those distinct patterns. And because the energy of every electron and every atom is different, they all have a unique fingerprint. So this is our modern understanding of it. Even back then, they knew that this was what they were working with. All right, so back to the eclipse, right? Tennant's team managed to get some absolutely insanely good pictures of the eclipse itself. So we're starting with thing 3 here, right? This is a photograph in 1868, right? I'm not a historian. I don't know when the photograph was invented, but it could not have been much long before this, right? And here we have a picture that rivals the resolution that I took with my DSLR, the last total solar eclipse, right? This is incredible, right? And got some really good measurements of the spectral lines of known elements, but they didn't make any revolutionary breakthroughs with the spectroscope, right? And in fact, he actually had a number of technical difficulties. And he noted that he could have done better if he had just accepted help from others that were nearby. Right? He said, Dr. Jansen had very kindly offered me the aid of the mechanic and tools that he had brought with him, and I should have done much better if I had availed myself of his aid. And he gives a little footnote here, which is as true then as it is today. The footnote here says, a good assortment of tools, a mechanic, and materials are very desirable in every way when one is so far from assistance. But having had everything attended to, I had no known wants, and I found, on attempting to select, that to provide for the possible wants would far exceed the sum I was authorized to spend. Right? So this includes 2 very valuable modern lessons. One, it doesn't matter what type of science you are doing, having a machinist that can work metal for you is incredibly, incredibly, incredibly valuable, right? When I was learning to actually build the instruments that I use, I would sketch what I wanted, which is great, made out of metal. I would take it down to the machinist, he would look at me, and he'd go, okay. And then he would flip it over and tell me what I actually wanted, right? Which was fantastic. And then he would charge me exorbitant sums that I didn't have to actually build it, right? So this is the other problem, right? Science was expensive even back then. This is from the Royal Astronomical Society, right? The Crown couldn't fork over enough money to do this. So, in any case, so this other chap here that he mentioned, Dr. Jules Jansen here, did make a revolutionary discovery using the spectroscope during that eclipse. Right? Using his own spectroscope, he observed not only those known lines, the known spectra of all the elements he was looking for, but also an unknown, brightly glowing line. Not a line cut out of the spectrum, but a glowing line superimposing itself on the spectrum. And it did not correspond to anything that he had seen before. Now, we know this because he talks about it later, but for some reason, maybe because he thought his eyes were deceiving him, he didn't actually report about it when he reported back to his higher-ups, which would be the French Academy of Science. What he did do, though, and he reported on this, was he actually, during the course of these observations, figured out a way to observe the corona of the sun without a total solar eclipse. which was great. So they brought the spectroscope to 1, looked at it, sorted out what they needed to do to block out the sun's light in the future, and now they could look at it whenever they wanted. Now, by coincidence, and completely independent of the eclipse, all the way back in England, right, this British astronomer here, by the name of Norman Lockyer, would also develop a method, a very similar method, to observe the sun's corona in a mission, to look at what was coming off of it, what was glowing, with a spectroscope without the need for an eclipse. Right? Lockyer, in his accounts later on, would actually bemoan the fact that the only reason that Janssen beat him to this breakthrough was because the dude that he commissioned to build his spectroscope got sick and delayed delivery. Right? Delayed delivery so much that Lockyer figured it out 2 days after Janssen. Now, they went on to have a wonderful agreement with each other. They took joint credit, right? Made sure that when they were presenting this, they talked each other up, which was absolutely fantastic, right? But he had developed this technique from his garden in Hampstead Heath in London, and he managed to observe the spectrum of the sun's corona. Now, I'm going to try the first audio here, so if it doesn't play loud enough, somebody please push a button up here. But I'm going to play an account here from his own readings. Maybe.
I began my work with the new my search after the prominences. I found that the south pole of the sun, I saw a bright line flash into the field. My eye was so fatigued at the time that I at first doubted its evidence, although unconsciously I exclaimed, "At last!" The line, however, remained an exquisitely colored line, absolutely coincident with the line C of the solar spectrum, and, as I saw it, a prolongation of that line. Leaving the telescope,
Actually, this was actually more common than it sounded. It was quite common for scientists and astronomers to involve their wives in their endeavors, often not just in a recording capacity, but in the cases of folks like Herschel. Herschel's wife, Caroline Herschel, was actually a better astronomer than Herschel was himself, right? Which is absolutely fantastic. What's up?
I think you got that wrong. It was his sister.
Oh, his sister. That's right, his sister. Thank you. Yeah, this is not Game of Thrones. So, in any case, here's what he saw, right? Here's that C line that he called, right? Now, this C line here at the bottom, this is what the absorption spectrum of this element is known to look like. Dark lines cut out of the spectrum. But at the top is the glowing bright line of C. Now, the C line is known, and they knew it at the time, to be due to hydrogen, right? Simplest element, something that is wildly abundant in the sun, right? But he made another discovery at the exact same time. An emission line that he initially labeled here as D3, right? Because it was very close to the D lines that were known to come from sodium. Right? Yet it was quickly realized by him, by Janssen, and by others that this line was not sodium, right? And in fact, it was not from any other element known to exist on Earth. So, later that year, right, they went and presented their results at the Palais de l'Institut de France à Paris. This is the French Academy of Sciences. And the new element was named for the Greek god of the sun, because it was observed in the sun. The Greek god of the sun is, of course, Helios, and so the name was helium. Right? Helium, an element that we know is the second most abundant element in the universe, that you all have in balloons, was discovered in space with very first time ores ever seen on Earth. Right, the first true cosmic cryptid. It was seen only by a few and only from a distance. We only have their word to take that this is what they were seeing. And that would last for many years, actually. So this was 1868. It wouldn't be until 1881 that an Italian actual geobiologist and meteorologist here, geochemist and meteorologist, Luigi Palmieri here, and only in the most extreme of conditions, in this case, the lava flowing from Mount Vesuvius, would another observation be made. He, of course, saw an inferno type. What he actually saw here, and he recounts this here, and I'll translate it instead of listening and having you read it in the original Italian. He says, "I collected some time ago an amorphous substance having a buttery consistency, gross, and a faded yellow color which had sublimated on the rim of a fumarole near the mouth of the eruption. Having analyzed this sublimated substance with a spectroscope, I recognized the lines of sodium and potassium and a very distinct linear line which corresponds exactly to D3, which is that of helium. For the present, I am making a mere announcement of the fact, proposing to return to this subject after having subjected the sublimate to a chemical analysis. The very first time that it was observed here on Earth. Right? Indeed, it wouldn't be until 1895 that a Scottish chemist